Hi students. So today we start lecture 66 in our aerospace engineering course, and today I am going to discuss the heating aspects as far as ballistic entry is concerned. So in the previous couple of lectures we were looking at things such as maximum deceleration. We derived the equation for entry into the Earth's atmosphere, and today we are going to look at the next problem, which is the heat generated when you enter the Earth's atmosphere. So let us look at two basic things which take place whenever you are entering the Earth, or it could be even a different planet. But in case it's the Earth, you are going to have certain situations. You are going to have a lot of deceleration taking place, and also there is going to be aerodynamic heating. Now, as far as maximum deceleration is concerned, it should be less than 10 G for the people in the manned vehicle, and in case you have an unmanned vehicle there should be no damage to any critical systems because the deceleration is too high. Now let's turn to heating because we discussed this deceleration problem in the last lecture. As far as heating is concerned, there are two situations which are possible. If you have a manned spacecraft, you need to have tolerable temperatures when you make the entry, and if you have an unmanned spacecraft, then you should not burn up or melt if you want to recover the spacecraft or the equipment or things inside the spacecraft. So this is the situation which we are going to discuss today. And to do that, we need to develop some model about the heating process as you enter the atmosphere, which will help us figure out how to design the spacecraft itself. Now, if we look at a typical spacecraft as it enters the Earth, it enters the Earth with a very high velocity. And what happens is that when you are flying high around the Earth, you have kinetic energy and you have potential energy because your speed is very high, your height is relatively high. And this is something which needs to be dissipated as you enter the atmosphere, and it should be ideally dissipated as heat into the surroundings through radiation and so on. So if we take the typical spacecraft, and you will see that generally they have a blunt nose, and today's lecture we are going to conclude why we have the blunt nose in a spacecraft. What happens is that you have the bow shock wave forming because, of course, remember this is entering at a speed much higher than the speed of sound. There is going to be a shock layer here, there is going to be boundary layers here, and there is going to be a wake here, and all the layers and wakes here are going to have very high temperature. So these are all going to be hot regions. There's going to be a lot of radiation taking place here also. Now, this body essentially travels with this very high velocity, and the bow shock acts somewhat like a shield to this body. So we are going to see why this body has to be a blunt body and should not be something like a supersonic fighter jet pointy nozzle in front or pointy needle in front. So to start the process, we'll start with something known as the Stanton number, and this is a dimensionless heat transfer coefficient. So this is given by CH is dq by dt divided by rho infinity V infinity H0 minus HW into S. So here H0 is the total enthalpy, HW is the enthalpy at the aerodynamic surface wall, S is the reference area, and dq by dt is the heating rate going into the surface. And this heating rate, which is the main parameter in terms of the heat transfer taking place, is something we are going to be very interested in. So we are going to try to get some expression for dq by dt and then the expression for q itself. So that's going to tell us the heat which is generated in the process of entering the atmosphere and finally landing somewhere on Earth. This heat is something which we need to estimate. Now let's look at the energy equation once again, which we derived many lectures ago. So this equation was given by H1 plus V1 square by 2 is H2 plus V2 square by 2, and also given that H is CPT, we can write this energy equation in this form. So this is the equation we are going to look at today, and we are going to now think about the total enthalpy concept. So what happens is that if you have a flow, let's say this flow has some velocity V infinity, the enthalpy is H infinity, and the temperature is T, and this is brought to rest to h0. So essentially at this point the velocity is simply 0 and the enthalpy is h0, so it is the total enthalpy of system. So this is similar to the definitions we did before in terms of total pressure and so on. So we can easily write this equation here. So all I have done is on one part I have set the velocity to 0. So h0 corresponds to velocity 0 and h infinity corresponds to velocity v infinity. So this is the equation I get for total enthalpy. Now typically v infinity is extremely high because you are entering the atmosphere at a very high velocity. So what happens is that we can actually write h0 as simply v infinity squared by 2. We can simply neglect h infinity. And one of the reasons is that h infinity would be Cp into T, and the temperature here in the far stream is relatively small compared to whatever temperature is associated with h0. So essentially we can neglect that temperature. So now let us look at the enthalpy at the wall, and the enthalpy at the wall is also much less than H0, or H0 is much greater than HW. And that's because as far as the wall is concerned, the wall temperature must always remain lower than the melting point of the material. So this is bounded by some pretty reasonable number. But the velocity upstream is very high, and therefore again H0 is very high. So we can say that H0 minus HW is almost equal to h0. So we are simply going to assume that, and therefore also we know that h0 is v infinity square by 2. So I can say h0 minus hw would also be v infinity square by 2. So now let's get back to the Stanton number and let's look at the heating rate. Now this is the definition of ch, and now what we do is we replace h0 minus hw by v infinity square by 2. So if we do that, then I get here Ch is dq by dt by rho v infinity square by 2 into s. So now this equation I can write it in this form here. I can take dq by dt to one side and the remaining terms to one side, and I get this very important equation. Now we are going to study this in detail because it's going to give us some idea about the heating rate. So the moment we look at this equation, we immediately realize that V infinity plays a huge role here because V infinity is to the power cube, and therefore what's going to happen is that the heating rate is going to be extremely dependent on the velocity. Already the velocity is high, and therefore you can see why the heating rate is going to be very high when the body enters the atmosphere at a high speed. Now, if we were to qualitatively look at dq by dt versus the altitude or height of the vehicle from the Earth's surface, what happens is that dq by dt at first increases and then it decreases again. So the increase is happening because as you are entering the atmosphere, the density is changing from 0 to some finite value, then it's going up, and in this region what's happening, the velocity decrease is sufficiently high that that is becoming dominant here. So essentially dq by dt also goes through a kind of maximum point here. Now we are going to use one more fact, and this is without proof, but it's something which comes from fluid mechanics, and this is known as the Reynolds analogy, which says that ch equals half cf, where cf is the mean skin friction drag over the entire surface. So if I use this definition here, I can write this dq by dt as 1 by 4 rho infinity v infinity cube scf. So all we did is replace ch by cf by 2 and we get this expression. Now cf is something we have a hold on compared to the Stanton number because we do know the skin friction drag coefficient. Now let's return back to the equation of motion for this spacecraft. So essentially remember from our previous lectures that the equation of motion was minus d plus w sine theta is mdv by dt, and we can assume w to be much smaller than d because d is proportional to velocity square. Velocity is very high, so this number d is going to be much larger than w. So therefore I can write minus d is m dv by dt, and I can write dv by dt is minus d by m. So this is the definition or the derivation of dv by dt, and if I then put the drag expression here, I get this expression here. So remember, drag is half rho v square scd, where cd is the drag coefficient, rho of course is density, v is velocity, and s is the area of the platform. So now with this definition of dv by dt, what I'm going to do is I'm going to use it in simplifying dq by dt. So dq by dt can be written as dq by dv into dv by dt by the chain rule of calculus, and then I'm going to put this dv by dt here in the next slide. So let's look at dq by dt again, which we obtained before, and I write this dq by dt as dq by dv into dv by dt, and so this becomes this expression into dq by dv. So all I have done is I've taken dv by dt as derived before from the equation of motion and have plugged it into this equation here. So I have got this nice looking equation in red here. Now what I can do is I can equate this dq by dt with this dq by dt because they represent the same quantity, and so I get this equation here. So one part is from this value and one part is this value. Now getting this has the advantage that I have removed time from the picture and I have expressed everything in terms of velocity here and q here. And there is also a lot of cancellation which is very beneficial for us. So rho infinity cancels out, s cancels out, the v infinity square cuts off and gives us a v infinity here and so on. So with all these cancellations, I get dq by dv is minus v m by 2 cf by cd. Now we'll drop the infinity subscript because we know what velocity we are referring to. We'll simply use v because it will help us in doing integrations and so on. Do remember, v here stands for the v infinity or the far stream velocity at which the spacecraft is coming in. So now we are ready for some integration. So we take the dq by dv. We can now see that this expression is something which we can integrate easily. And what we are going to do is we are going to presume the spacecraft enters the Earth at velocity v is v infinity ve. So this is the velocity here, the entry velocity, and at that point the heating is simply 0. And when you reach this point here where velocity is 0, q is q total. So this is the total heat. So we are going to calculate this total heat. So to do that, I write this equation in this form and integrate it between 0 at VE and QT at 0. So this is basically in terms of the velocity, and so of course I immediately know the integral of V is V square by 2. The negative sign will go away because the integral is from 0 to VE. So if we flip this integral, then the negative sign goes away. So I get this equation here, which is the integrated form, which is given me the total heating Q dot is half Cf by Cd m by 2 Ve square. So now this equation is very important, and this is giving you a nice closed form solution which tells us the total heating generated during the landing process of the entry vehicle from V equals Ve to V equals 0. And I can immediately see that this is dependent on two factors. One of the factors is of course the VE itself. So we can clearly see here that mVe square by 2 represents the energy of this body when it enters the earth. So that's the kinetic energy which is initially there. And one of the ways to remove this or reduce this total heat would be to reduce VE as much as possible. So that's the obvious solution. You want to enter at a lower velocity. Now the second solution has to do with reducing CF by CD because Q dot is also proportional to CF by CD. So that's what we are going to look at next. So if we look at that part, so we are going to find out how to get the minimum total heat Q dot. So this is proportional to CF by CD, but recall CD is CDP plus CF, CDP being the pressure drag and CF being the skin friction drag. So I can write Q dot in this form here. Now if I look carefully at this equation, what I could do is I could try to maximize this pressure drag, and that is actually going to bring down this Q dot value here. So interestingly, one of the ways to reduce the heating is to maximize pressure drag. So we can see here that the objective is to minimize this CF by CD value, and we can look at what would happen for two different cases. For example, let's look at a slender body and let's look at a blunt body. So in the case of a slender body, the pressure drag is going to be low, and therefore this ratio is going to be approximately equal to 1 because there is not much separation out here and so on. So what happens is that CF by CD is approximately equal to 1, but for a blunt body the pressure drag is high, and therefore CF by CD is going to be much less than 1 because CDP is a very large number because of all kind of separation here. So this actually tells us that having a blunt body is better when you are entering the Earth's atmosphere in terms of heating and so on. And if you see any vehicle which has been out in space and is returning back to Earth, it has this kind of front nose. So it's not a pointy front nose, it's actually a blunt nose. And also there is a lot of material science at work here in terms of the high temperature materials and so on. You may be using ceramic metal, composites and other material here. So let's now pictorially look at the different type of vehicles we have considered. We saw that when you are in subsonic flight and high subsonic speeds, typically for passenger jets and so on, you have a reasonably nice shape here, which is very amenable to nice flow about the aircraft. However, when we go supersonic, we have this kind of pointy nose, and the reason is that you want a shock wave to form here, and so behind the shock wave there is a dramatic reduction in the airspeed. Now, if you go to this kind of vehicle which is entering the earth, you again have a blunt nose, and this blunt nose is even blunter than the nose here. This is a regular aerodynamic shape, but this is as blunt as you can make it. Now this of course is a vehicle which has to go and land in the earth, so it's relatively less blunt because it's a vehicle which would have multiple design requirements here. This has to fly in the atmosphere and out of the atmosphere. But if you have vehicles which are simply landing, then you will have a really blunt nose of the type I showed in the first few slides. So let's recapitulate what we learned today. We essentially started with the Stanton number CH, and from that we were able to get the expression for dq by dt, and we saw that it's proportional to V infinity cube. So the heating is extremely dependent on the velocity at which you enter. We then use the fact that CH is half CF, the Stanton number in terms of the skin friction drag, and then we were able to write dq by dt in this form, and then finally we got q total in this form here. So that was the total heat generated from the point you entered the Earth's atmosphere at velocity VE to the time you landed at velocity V equal to 0. So here of course the Q total is dependent extremely on velocity here VE, and also it depends on CF by CD, which is the ratio of the skin friction drag to the total drag. Now one of the ways you can minimize Q dot is reduce VE itself, or you can reduce CF by CD, and for reducing CF by CD what you can do is that you choose a blunt body so that the CDP is high, so that the pressure drag is high, and therefore what's going to happen that this is going to be lower. So that's the reason why blunt bodies are selected as far as landing is concerned or re-entry of space vehicles into Earth is concerned. So now we know the basic preliminaries as far as spacecraft is concerned. We have figured out things such as the orbit equation. We have learned the entry equation, the heating generated, the maximum deceleration, and so on. So essentially, you now have a good deal of knowledge about how spacecraft are designed and the basic ideas about space vehicles, about orbital mechanics, and so on. And so, as far as this course is concerned, we are going to end this subject here, and then we are going to take off into some different areas. So, maybe I will spend some lectures into structures and materials, and maybe then we are going to look at aspects about more deep things into flight dynamics. So that's something which I'm going to do next. So if you have not subscribed to my channel, please do so. Even if you are seeing only these videos, it's always good for YouTube to know that the subscription rates are going up because they give more importance to the channel, and also like the videos, because again the YouTube algorithm likes to see that the videos are being liked. So I'll end this lecture now and I will see you in a video sometime soon. See you then.